Hi, everyone. Welcome back to the final stretch of the second day of Sub0. I hope you enjoyed the music on your break. Now we have William Freudenberger from Kilt Protocol, who will be discussing limited delegated proof of stake in the Polkadot ecosystem. William?
Yeah, hi. Hi, everyone. Thanks for tuning into this presentation. As Bill said, I'm also William Freudenberger. I work for Kilt Protocol as a software engineer and a product owner. And yeah, I'd be happy to present our limited delegated proof of stake solution for Parachains. So in the next 20 minutes, I will first recap consensus mechanisms and compare nominated proof of stake with delegated proof of stake and our limited delegated proof of stake by taking a closer look at the implementation differences of Parachains NPOS, Moonbeam's DPoS, and our LDPoS. And as we learned a lot on our road until completion, there's hopefully valuable information that I would like to share with you before I conclude with the outlook. Yeah, so as most of you know, consensus is mandatory for distributed systems like a decentralized blockchain because there's no central service which maintains the state, and there are several approaches on how to provide fault tolerance. Proof of work and proof of stake are the most popular ones among these. And in my opinion, comparing both helps to understand the motives and incentives behind proof of stake. The main goal for both is, of course, the security of the network. And that does not only mean that the nodes agree on state transitions, but also that data availability is ensured at all times. And as a reward, native currency is issued to the block authors, which obviously creates competition to get that. And in proof of work, this is to have a sufficiently large hash power because authoring a block is decided by a fair lottery among all participants, depending on the hash power. And in proof of stake, as the name implies, you actually compete with your stake. So the security of the network is proportional to the amount of stake tokens. And usually only a limited number of the top staked candidates are then chosen to become the set of block authors for a certain period of time. And among this temporarily fixed set, the block authorship is evenly distributed between the participants, sometimes independent of their stakes within this set. Fortunately, this limited pool with the slot-based authorship like Aura that we know as Substrate engineers creates new security issues, which basically don't exist in proof of work. On the one hand, we have equivocation, which happens when you assign two blocks at the same height. And on the other hand, we have the unavailability issue if some of the block authors are offline when they should author a block, and then they miss to do that. In proof of stake, proof of work, as mentioned, both scenarios are very unlikely and are basically fixed by everyone competing with each other for every block, which results in a probabilistic finality. And I know this is all very, very simplified, and we could speak days about it, but the sake of this presentation isn't the comparison, but proof of stake. So I would dive deeper into proof of stake now, namely by comparing nominated proof of stake with delegated proof of stake, again, on a very high level. Both approaches mainly differ in their complexity and the security they want to provide, or they provide. Delegated proof of stake is a very simple solution. You directly stake an amount of tokens on a single candidate. You might be able to do this multiple times. And for the election, you could just sort all of those candidates by their total stake and then take a slice out of that to have your collator set. In nominated proof of stake, you instead stake your tokens on a set of candidates, and then an algorithm automatically distributes your stake to your chosen candidates every time a new pool of validators is chosen, such that the security of the network is maximized according to its rules. And in Polkadot and Kusama, this algorithm is fragment, and it tries to solve a very complex nonlinear optimization problem by maximizing on the one side the total amount at stake, while also minimizing the variance of elected validators, because these cause a good risk to the system. And a lot of developers might ask themselves now, okay, if nominated proof of stake is proven to be working, also maintained and more secure, why would the Parachain team actually put in sweat and time and hard work to develop their own consensus? And the answer lies in Fragment, because Fragment is overkill for Parachains, which have much looser security assumptions than the relay chain. And it could in fact stall your parachain due to its complexity, which leads to big, or potentially leads to big POV sizes from inherent executions. As a parachain, you basically only need to ensure that you have at least one collator that is honest and provides the data, and the correct state transition are ensured by the relay chain. As the downside for the parachains, you have more rigorous restrictions on your throughput, and you can actually stall if you exceed this POV size, the proof of verification size, sorry, from those inherent executions. And for us, this was the motive to develop our own staking consensus, because if you stall due to this issue, this can only be fixed by a runtime upgrade initiated by the governance on the relay chain. So when we designed our LDPoS, or limited delegated proof of stake consensus, we had three main goals, which are quite simple. One, we wanted to ensure data availability in a redundant and robust manner at all times. Of course, we want to be decentralized, and we want to ensure that we have at least one honest collator. And as an incentive, as others, we reward those collators with native tokens. Also, in the early lifetime of the network, we also reward delegators to stimulate the decentralization and filter this pool of candidates for honest, trusted, and well-performing collators. And to support a sustainable long-term growth of the ecosystem, we also decided to have some inflation, but it was very important to us to keep this basically as low as possible and mathematically bound. So as a result, we derived three design principles. We definitely did not want to limit the number of collator candidates, but there is a minor restriction that to be considered a candidate, you need to stake at least 10 kilo kilts, so 10,000 kilts. What we wanted to limit was the pool of collators though, and this is updated every 2 hours, which is 600 blocks for a parachain. And it was also important to us that the rewards should be paid out immediately to the block authors and their delegators after authoring a block without any restrictions. So not a lock or whatever, it should be available immediately. And to compensate the cost for running the collator hardware and maintenance, we also decided to split the reward configuration for collators and delegators. For now, we have 10% reward rate for collators, and for delegators, there's an 8% reward rate. This will change over time, but this is the current state. The clicker, sorry. So yeah, so far we have basically just described a delegated proof of stake consensus, and we call this limited because we bound on the one hand the inflation, which only comes from the block rewards. Also the maximum amount a collator can stake, the number of collators, and the delegation reward period. And because the parachain POV size issue was the main motive to design our own consensus, our main focus was to have very lightweight inherent executions, which we partially achieved by working without any snapshots. So we always use the current data when, for instance, updating the collator pool. As mentioned, we also have a constant reward rate for instant block rewards, and an implementation detail. We are already using the bounded structs such as the bounded VEC or the bounded binary tree map for the on-chain storage, which will be required once there are POV benchmarks, which I hope happens as soon as possible. I hope this little this made you somewhat familiar with proof of stake until this point, because in the next slide we will compare Parachains staking solution with ours and Moonbeam's. And as a note before I start with that is that our implementation is actually based on Moonbeam's solution. Eventually, both implementations diverged quite heavily, in my opinion, but I definitely wanted to shout out and thank Moonbeam at this point for their great work. Yeah, thank you. So, oh, forgot to click here, sorry. So what we see in this table here is my attempt to compare all three systems at a very high level, while also paying attention to those inherent executions I was talking about. And these are displayed in the first two rows. Let's start with the executions in every block, which I generalized with the onInitialize hook in the first row. So when I say frame staking, so I was probably switch sometimes, but frame staking I refer to as the Polkadot and Kusama relay chain LDPoS solution. And yeah, I hope this will be understandable. So in the on the relay chain, there's just a single storage read for the current era in onInitialize. So this happens in every block. So their complexity is constant, while we, as mentioned, reward the author in every block. And since we allow delegations to a validator or a collator, our complexity is linearly dependent on the number of delegations, which is here denoted by the letter M. And in Moonbeam, they check whether their collator actually has block author membership with binary search. So they have logarithmic complexity. And so far, the differences seem to be negligible if the maximum number of delegations and collators is not too high, but this will change when we take a look at the next row, where we take a look at the start of a new session, which is every time when new validators are elected. As mentioned in the relay staking, this is done by Fragment, which is very complex. On a very high level, you could say that for each election seat, so for each validator for this time period, you iterate over all the possible candidates and their nominations. So the complexity is somewhere between quadratic and cubic, depending on the maximum number of candidates and max nominations. And I know this is very simplified, but yeah, Fragment, you could speak days about Fragment and still not understand it. In our case, we just do a single storage read. We just query the current collator pool. And we can do this because we actually update the collator set in any staking extrinsic. So anytime a collator or a delegator joins or leaves or changes their stake by increasing it or decreasing it, we update the current best collator candidates. And as mentioned, we don't use snapshots. So we always have the current best collator set and can just do a storage read. And this is possible because we pass this complexity to the user extrinsic instead of executing them inherently, as is done in Moonbeam, where after a session, they pay out all the collators and their delegators and also recalculate the top candidates. So as you can see, due to our tricks of not using those snapshots and passing along complexity to user extrinsics, our inherent executions for staking are, I would say, indeed very lightweight and only dependent on the maximum number of delegations for a collator, which is exactly what we wanted to achieve. And apart from that, also comparison-wise, we, as mentioned, we pay out rewards immediately, whereas in the relay staking and in Moonbeam, you receive points based on your block production participation, and those points are then converted to rewards at the end of a session. Also, in our system and in Moonbeam, those payouts happen automatically, whereas in the frame staking, you need to actually call an extrinsic for each validator. And then when you call that extrinsic, the validator and their nominators are paid out. And that to me makes sense because they allow for far more nominations per validator than we do per collator. And last but not least, the staking method, also interesting to look at in the relay staking. And in our, we just lock tokens. So you can still use them, for instance, for governance voting, whereas in Moonbeam, they reserve. So these tokens can't be used for any other reasons. Yeah, and this already concludes this high-level overview of those 3 different staking solutions. As mentioned, we have definitely learned a lot, especially about parachain design principles when building the code base. So I hope that you can benefit from our knowledge that I would now exchange with you. Let's see. Okay. Oh, this is the different slide. Sorry. So yeah, let's first talk about 2 metrics, the 2 metrics for block production. On the one side, we have here the block execution time, which should be at most 500 milliseconds for parachains or 2 seconds for the relay chain. And I don't know whether you listened to the previous talk, but it was about weight calculation. And this is the factor for this block execution time. Because in order to measure the execution time of your transaction, Substrate introduced this concept of weights. And in other words, the weight of a transaction reflects the required CPU time for executing it. So it is crucial to execute your weight benchmarks on the minimum required hardware for running a collator. Because if you run them on a high-end machine, all those users with lower hardware might take more time than they should by the definition of the system. And then you can end up exceeding the block execution time. And if this happens, your parachain is not completely stalled. You might have 1 or multiple transactions inside your transaction pool whose weight is too low, considering the effort to execute them. And in the worst case, you won't produce a block until the mortality of these transactions is reached and they are gone from the pool. So in this regards, you should always remember to have accurate benchmarks on your minimum required hardware. Much more critical, however, is the second constraint here, the block POV size, the proof of verification size, which should be at most 5 megabytes. And if you exceed this with inherent executions like on initialize or on finalize, your chain is bricked. This is because the relay chain rejects the block that you just produced. And because you do this automatically, your parachain tries to produce the same block again. And then you are in a loop and there is no fallback mechanism. You can only fix it by a relay governance runtime upgrade. So this also is a particularly issue for parachains because on the relay chain, you have a somewhat flexible block time and the relay chain doesn't stall if the POV size is exceeded with those inherent executions. It will just take longer to produce the block. Whereas on the parachain, block time and the POV size are both hard caps and a block is just not built if these requirements are not satisfied. So I highly recommend don't overload your on initialize or on finalize or even use session hooks and try to prevent any read or write in those inherents, which is not necessary. And if try to move it to extrinsics, which is then paid by the user. As mentioned, the first constraint is handled by weight benchmarks. And for the second one, there's an open issue to add POV benchmarking. I hope this will be merged as soon as possible. So we are more aware of how to deal with those POV sizes. Now we move from something which you should pay attention to something that, in my opinion, is nice to know. And that is the order of pallets involved in the process of assigning and noting block authors. To me, one big aha effect was when I learned that there's actually a delay of 2 sessions when you change your validators within a session. So this doesn't happen instant and this cannot happen instantly. In the order first comes the aura pallet, which just takes a list of account IDs as input and uses actual timestamps, not block numbers, but timestamps, to assign each of these authorities to their slot. And then this order is kept over multiple iterations until a new set of authorities is chosen. And Aura can also map those, can map indices of the authority set to their account IDs, because the other pallets usually just use those indices as they are more lightweight. Then the session pallet checks whether a new session should start, and those implementation is done in staking or wherever you want to have it. And if so, it assigns the validator IDs and session keys, which were actually set at the beginning of the previous session, to the current authorities. And then it retrieves new validator IDs and session keys, also from staking, for the next session. Then in the staking pallet, we just update our round, which is just an internal data structure that is used to trigger a new session, doesn't do any other magic. And the authorship pallet then handles the rewarding of the block author by the node author hook, which is also implemented inside staking. Yes, okay. So this about the order of those, or the how they deal with it, but it's also important how you order those pallets inside your construct runtime macro, because you can actually run into problems if you don't order them correctly, as we did. Here we see an error that we ran into and didn't know really how to debug it until we took a closer look on the order of our pallets in the construct runtime. So we solved this issue of the invalid authority set by changing the order of the authorship pallet. And as I dug deeper into this issue, I learned that the onInitialize actually runs in the reverse order of the declaration of your pallets in the construct runtime. So in our example here, the onInitialize of Aura X would be first, then Aura, then session, then Parachain staking, and then authorship. And if you if a pallet implements a hook, in our case staking, and the hook was the node author hook, and this hook is run in an onInitialize function inside another pallet, in this case authorship, then the pallet in which the hook is implemented, so staking, needs to be defined after the pallet in which it runs an onInitialize, which I didn't know. So yeah, just by fixing this order of the pallets, we got rid of this error. At least we assume it, because we never encountered it again. So I hope I did not run completely super lightning fast through all of this content. I know that the time is almost running out, so sorry if I was too fast. I will be in the Discord afterwards for questions, but I still want to share our outlook here, what we are planning next for our staking. Our biggest priority is that we want to add slashing, but unfortunately, those equivocation checks are not available for Aura. They are available for Babe, but Babe is not supported for Parachains. So yeah, we are, let's say, a bit blocked there if we don't put effort into this on our own. Apart from that, we definitely want to scale up delegations. Right now, we allow 25 delegations per collator and only 1 delegation per delegator. This is planned to increase, but since our network just launched, we wanted to start with a secure setting. And last but not least, we also want to decrease those extrinsic weights to lower the transaction fees and also enable even more scaling up in the long term. Then there is this beautiful slide that our legal department asked me to share with you. You won't have time to read it all, sorry. It basically says that the information I just shared with you is just a technical presentation and shouldn't be considered exhaustive. If you would like to read through the text, I already shared the slides in the Discord, so you can have a nice read if you would like to. And yeah, then I would just I hope that you learned something from my talk, from my presentation. Thank you very much for listening, and I'm happy to answer some questions now and then afterwards in the Discord. Thanks a lot.
All right, thank you very much, William, from one bill to another. So we did have a question. Can you make the payouts a user callable extrinsic or otherwise make that configurable?
In which regard configurable?
So I think the idea is make it so like a pallet where you can decide whether or not when the developers are setting up the runtime, if the payouts are user callable extrinsic or happen automatically. That's how I'm interpreting it.
Okay. So if someone took our pallet, they would like to make it configurable. Right now, I would say this wouldn't be supported because it's quite deeply nested inside the code. If you make it configurable, so if you want to allow it for to be either delayed or not, this would be quite a complex change in my opinion. And I learned that you shouldn't delay anything which you don't necessarily need to delay. Yeah.
Okay.
So I would say it's quite difficult. Yeah.
Okay. Yeah. Thank you very much. And I think if there are more questions on that, or I misinterpreted the question there, I apologize. But I'm sure you can talk in the Discord after this.
Sure.
All right. All right. Well, that's the only question that we have. So once again, thank you very much.